Let's talk about a mysterious failure in deep space. A story about how two simple pieces of metal, just by touching, could sabotage one of the most ambitious missions we've ever launched. But stick with me, because that same exact principle, well, it might just be the key to building entire cities on other worlds.
Okay, let's wind the clock back to 1991. NASA's Galileo spacecraft is hurtling toward Jupiter. We're talking a $500 million mission, a huge deal, carrying the hopes and dreams of a whole generation of scientists.
And pretty much everything, all the data, all those incredible images we hope to get, it all hinged on one single mechanical action. This massive 16-foot wide antenna had to unfold perfectly, like a giant umbrella, millions and millions of miles away from any human help.
But when the time came and the command was sent, nothing. The antenna was completely stuck. For days, then weeks, then months, engineers on the ground tried everything they could think of to get it free. But out there in the freezing vacuum of space, it absolutely refused to budge.
That one failure absolutely crippled the spacecraft. Galileo had to complete its entire mission using this tiny little backup antenna. And that meant beaming its precious data home at a pathetic 70 bits per second.
Now, to put that number into perspective, because 70 bits per second doesn't sound like much, and it isn't. Take a look at this. It was over 2,000 times slower than one of those old dial-up modems from the 90s. You know, the ones that made all that noise? Yeah, this was a catastrophe for the mission's science goals.
So what happened? After a long investigation, they found the culprit. It wasn't a software bug. It wasn't a broken part. It was something weirder. Two small aluminum pins in the antenna mechanism had simply fused together. No heat, no glue, no welding torch. They had just become a single solid piece of metal. So what in the world is going on here? How can two solid objects just merge? This gets us into some really cool fundamental physics.
The phenomenon has a name. It's called cold welding. And yeah, it sounds like something out of science fiction, but it's very real. It's a process where the atoms on the surface of one piece of metal literally reach out and form a permanent metallic bond with the atoms of another piece. They become one.
So you're probably wondering, okay, why don't my car keys fuse together in my pocket? And that's a great question. The answer is our atmosphere. Here on Earth, the moment a fresh metal surface is exposed to the air, an incredibly thin, invisible layer of oxide forms on it almost instantly. Think of it like a super thin layer of rust. And that layer, that contamination, acts as a barrier, physically preventing the pure metal atoms from ever actually shaking hands.
But space is a completely different story. It is an almost perfect vacuum. As you can see on this chart, the pressure is incredibly low. At those pressures, that protective oxide layer, along with any other tiny contaminants, basically just evaporates away, leaving the metal atomically pure and ready to bond.
And here's the real kicker. It turns out some metals are way more prone to this than others. And when you know it, the list of the worst offenders, we're talking gold, aluminum, copper, these are the exact same materials we love to use to build our spacecraft because they're lightweight and great conductors. Their specific atomic structure just makes them extra sticky in a vacuum.
So you might think Galileo was just a case of really bad luck. But nope, not even close. This has been a quiet, persistent problem for as long as we've been going to space.
This problem has popped up again and again and again. Back in the 90s, the docking probes on Soyuz capsules visiting the Mir space station started getting stuck together sometimes. Then in '97, a door on an instrument on the Hubble Space Telescope showed signs that its surfaces were starting to weld themselves shut. It's been this quiet saboteur for decades.
And hey, don't think this is some old problem we've solved. Just this year, in 2024, the European Space Agency tested 30 common satellite hinges in a vacuum chamber. And the results are, well, they're kind of terrifying. A full 2/3 of them failed, 67%, all because of cold welding. The sticking force was up to 5 times stronger than what the hinges were designed to handle.
So for this whole time, we've been talking about cold welding like it's the bad guy, right? It's a flaw, a bug, a problem to be solved. But this is where the story takes a really cool turn. What if we've been looking at this all wrong? What if we just flipped the script? Instead of fighting this fundamental law of physics, what if we started using it? What if this invisible destructive force is actually the key to building our future in space?
I mean, just think about what cold welding offers. You get a perfect, seamless bond that's as strong as the original metal itself, and you get it with no heat, no electricity, no welding rods, no glue, no extra anything. Here on Earth, that kind of bond takes a ton of effort. But in space, it's just what metal does naturally. It's the default setting.
And this isn't just a cool idea. People are working on this stuff right now. On the International Space Station, there's an experiment to use vibration to cold weld patches over tiny meteoroid holes. NASA is looking at creating a lunar forge for the Artemis missions, using the moon's vacuum to weld structures together. And down the road, we could be building massive, kilometer-wide space stations out of panels that just fuse together as soon as they touch.
It's an incredible thought, right? The exact same physical law that crippled the Galileo probe could be the very thing that lets us build cities on the Moon and Mars. It's just a powerful reminder that engineering isn't really about fighting the universe. It's about understanding its rules well enough to use them. The universe isn't malfunctioning, it's just following the laws of physics. The only question is, are we smart enough to work with them?